Hey everybody, Dr. Duncan here. This is a supplemental video lecture to the assigned readings and the Simutext exercise on climate change. Simutext will cover most of what you need to know about climate change. In this lecture, I want to add some context and a few details to better understand the concepts and facts presented in the Simutext exercise. Specifically, I'm going to touch on RCPs, tipping points and hothouse Earth scenario, social impacts, the Paris Accord, and suggestions for learning more. It doesn't matter whether you watch this lecture before or after the Simutext exercise, but I do suggest you will get more out of it if you be sure to watch it afterwards. Climate change will be one of the most important influences on your professional and personal life. And as you learn in the Simutext exercise, it will have tremendous impact on Earth's ecosystems and biodiversity. It will affect the future evolutionary pathways of most species on the planet, and for many, it already has. I want to add some more depth to the content provided about global climate models, because the outcomes of these models will have tremendous bearing on our future. As you learn in the Simutext exercise, climate scientists develop computer simulations to model Earth's complex climate. The models are built using over a century's worth of observational data on the climate. Once models have been built and can reliably predict the climate under conditions we've seen in the past, scientists then use them to make predictions about the future. But which future? We have many futures ahead for us based on whether and how quickly we begin reducing greenhouse gas emissions. As is briefly mentioned in the Simutext exercise, climate scientists have tackled this issue by predicting different futures based on greenhouse gas concentrations in the atmosphere and how much heat or net radiative forcing this causes. These future scenarios are called representative concentration pathways, or RCPs. Each represents a different future of greenhouse gas accumulation in the atmosphere based on our use of fossil fuels. This figure shows assumptions about greenhouse gas emissions with each of the RCPs over time. The x-axis shows the future by decade, and the y-axis shows the amount of greenhouse gases in the atmosphere. Note that the y-axis is labeled in CO2 equivalents. Instead of developing an RCP for every different greenhouse gas, all greenhouse gases are represented here by converting them into the equivalent contribution to warming that a CO2 molecule has. For example, one methane molecule traps as much heat as about 21 carbon dioxide molecules. Thus, if we had 10 methane molecules to account for in a model, we'd convert them to 210 CO2 equivalencies. Okay, let's look at the RCPs on the graph. What we are looking at here is not a forecast, it's only showing the assumptions about greenhouse gas emissions over time for each RCP scenario. The number associated with each line represents how much heat trapping potential our greenhouse gases have caused in the atmosphere. If you have done section 3 of the Simutext exercise, you learned about radiative forcing in the atmosphere. The numbers associated with each of these RCPs represents the net addition of radiative forcing, or heating, in the atmosphere under each scenario by the year 2100. The units are in watts per meter square. The red line, RCP 8.5, shows what's known as the business as usual model. This represents the future atmosphere if we fail to reduce greenhouse gas emissions and continue to emit them at our current rate of increase. That rate, by the way, has been accelerating in recent years when it ideally would be slowing down. The green line represents an optimistic RCP that would have led to only 2 degrees Celsius of warming. Unfortunately, we are diverging from that possible timeline because we're not reducing emissions quickly enough. That said, it's not too early to give up on limiting warming to 2 degrees Celsius. I'll circle back to the importance of this in just a few moments. Okay, up to now we've only looked at graphs of the assumed greenhouse gas emissions for each of the RCPs. I want you to see how RCPs are used to inform us about possible futures. So in this slide, we'll examine the predictions of how much warming will occur with each pathway. Here we see 2 graphs. The top graph is basically the same one we examined in the previous slide. The bottom graph shows 3 of the RCPs and associated change in global mean temperature. Note that temperature is measured in Fahrenheit. Sometimes we get graphs from scientists that are in Fahrenheit, sometimes they're in Celsius. The other thing to notice about graph B is that areas of the graph are colored. These colors represent the range of global climate model outputs associated with each RCP in terms of 95% confidence intervals. The lines represent the average predictions for that RCP. Okay, now that we understand how the graph works, let's understand what it means. First, let's look at RCP 8.5, the pathway known as the business as usual model. If we continue burning fossil fuels as we have been in the last few years, we're projected to see 8 degrees Fahrenheit of warming, or 4.4 degrees Celsius of warming, by the year 2100. Let's hope we don't go there. Most models suggest this would be a catastrophic level of disruption to the biosphere. Instead, let's work towards RCP 2.6, where at the year 2100 we're looking at about 2 degrees Fahrenheit of warming, or an additional 1.1 degrees Celsius of warming over last century. That's still a lot of warming for our planet, but there's a good chance we can avoid many of the most severe impacts. So why did just a few degrees of climate change matter so much? To answer this, I want to spend a bit of time looking at what is at stake if we continue on the RCP 8.5 track. These next few slides show us where we're probably headed if we keep going on that pathway. What you see here is a graph where the axes run through the middle of the graph instead of on the sides. The y-axis, or vertical axis, shows temperature change in degrees Celsius, and the x-axis, or horizontal axis, shows sea level relative to pre-industrial levels. As you learned in the semi-text exercise, as average global temperatures rise, sea level also rises because of the melting of polar and glacial ice and the expansion of water as it warms. The looping curves on the graph illustrate how Earth varies in temperature and sea level over geologic time. At some point, you've probably learned about the ice ages. This was a period of Earth's history from 2.5 million years ago to about 10,000 years ago. This was a very cold time for the planet, interrupted periodically by warm conditions similar to today. These climate oscillations were caused by the Milankovitch cycles that you will learn about in semi-text. Sea level would rise and fall dramatically as the climate warmed and cooled over and over. The difference in average temperature between today's climate and an ice age is just a few degrees, which illustrates how responsive the planet is to cooling and warming. Ice ages are represented in the lower left portion of the graph. This arrow shows Earth when it is leaving a warm interglacial period and entering another ice age. At that time, the climate is cooling and sea levels are dropping. This next arrow is where Earth would be during the peak of an ice age, when temperatures were very cold and sea levels were much lower than today. This arrow illustrates where Earth pulled out of the last ice age. From here, Earth enters the Holocene, that period of 10,000 years up to now with mild and stable temperatures. Now, thanks to greenhouse gas emissions from the burning of fossil fuels, Earth is here. We have begun moving in the direction of a climate that Earth has seen many times in the past, one that is called hothouse Earth. This is the future that RCP 8.5 business as usual scenario is likely to cause. If we get stuck in this cycle, Earth will warm considerably over the next century and beyond. All polar and glacial ice will melt, and sea levels will rise dramatically. Instead, we need to move back here, bending the climate back to something like we had during the past 10,000 years of the Holocene. Let me put our predicament in this context by relating our current conditions to past conditions. Already, the Earth's concentration of CO2 in the atmosphere is at about 415 parts per million. The last time carbon dioxide levels were over 400 parts per million was the Pliocene, some 3 to 5 million years ago. During that time, the Earth was 4 to 7 degrees Fahrenheit warmer. That's 2.2 to 3.9 degrees Celsius. And those temperatures are relative to the pre-industrial age. During that time, sea level has been estimated to be 72 to 82 feet higher than it is now. We are already at 1.1 degrees C higher than pre-industrial levels in 2020. The last time Earth was as warm as it is now was some 129 to 116,000 years ago during the ice ages, during an interglacial period when sea level was 20 to 30 feet higher than today. Just 4 to 6 feet of sea level rise this century is enough to cause catastrophic disruption to society, let alone ecosystems and biodiversity. Major cities in the US and throughout the world would be inundated. This is not the future we want, nor the one that we want to burden future generations with. This is a three-dimensional visualization of some of the same information that we just saw. The x-axis, which crosses left and right, represents how hot or cold the Earth is. The vertical axis represents climate stability. The higher on the graph, the more stable Earth's climate is. The lower on the graph, the more unstable. There is a third axis here, one that travels toward and away from our perspective. It represents time, with the future and current time being close to us and distant times farther away. Check out the distant Earth ball in the back, the one that's closest to the top of the slide. That represents Earth during the Holocene, a time when Earth was warm, not cold like the Ice Ages, and not hot like a hothouse Earth situation. Earth was also stable in the Holocene, resting in that little notch of the graph. But as we moved forward through time, and we started deforestation and then industrialization, we added greenhouse gases to the atmosphere. Today's situation is represented by that Earth in the center right of the graph. From here, we have two directions we can go. If we keep on going like we're doing now, the RCP 8.5 pathway, we'll likely hit a planetary threshold where we plunge into a hothouse Earth climate. Climate scientists estimate that we will be very near this threshold when we warm the atmosphere by about 2 degrees Celsius above pre-industrial levels. Scientists further warn that at or near 2 degrees Celsius, we may hit tipping points in Earth systems where we trigger runaway positive feedback cycles that cause escalation of climate change beyond our control. As I mentioned earlier, we are already at 1.1 degrees Celsius above those pre-industrial levels here in the year 2020. What climate scientists and others are recommending is that we quickly and dramatically reduce greenhouse gas emissions and steer Earth's climate back to the stabilized Earth climate of the Holocene. That's represented by Earth that is closest to us on the graph. All this illustrates why many scientists and others, myself included, are very concerned about climate change. A lot is at stake, and what happens in the next decade will determine the living conditions for humanity for centuries to come. According to the Intergovernmental Panel on Climate Change, which is the planet's leading authoritative science group on climate change, the world's carbon emissions have to fall by 45% by the year 2030 to keep the world's average temperatures from rising more than 1.5 degrees Celsius above pre-industrial levels. Thus, we have less than 10 years to institute some significant changes in how we power our economies and how we live. As I suggested when I mentioned sea level rise, there's a lot more at stake than species migrations, ecosystem disruptions, and extinctions that we learned about in the semi-text exercise. Climate change is already disrupting and harming our health, culture, and economy. Climate change is forcing people in the United States and around the world to move away from areas that have become uninhabitable due to drought, flooding, and in some cases, heat. What you see here on this slide is a small selection of the many other threats to our health, safety, and ability to prosper. Since many of you are going into healthcare, I'll point out that there are many health impacts of increased temperatures, including heat-related illnesses, increased disease spread, and declines in air quality. It's also important to understand that climate change is having a disproportionate impact on the poor. Ironically, it is not the poor that are causing climate change. Most fossil fuels are burned to support the lifestyles and economies of the middle and upper classes around the world. This imbalance is at the heart of the dialogue about how to develop fair and effective policies to respond to climate change. So what's being done about climate change? Many cities, corporations, and citizens have committed to reducing their reliance on fossil fuels and are switching to more sustainable modes of living and working, especially through switching to renewable energy sources that have low carbon emissions. The state of Virginia, for example, has committed to being 100% carbon emissions free by the year 2045. These are important steps, but we do need broader action at the level of national governments. The latest international effort to cooperate to slow and ultimately reverse greenhouse gas emissions is the Paris Accord, adopted by the United Nations in 2015. Previous treaties, such as Kyoto, failed to bring unity in action because of disagreements on setting mandatory targets for emissions reductions. Much of the tension arose from disagreements between the poor and the wealthy nations of the world. Developing nations wanted to fully modernize their economies and have been drawn to fossil fuels as the energy source to rely on to industrialize. They reasonably argued that developed nations, such as the United States and most of Europe, all of whom modernized using cheap fossil fuels, these nations should help pay for developing nations to adopt renewable energy technology. Many developed nations, including the US, refused to agree to these terms, mainly citing economic concerns. The UN delegations that crafted the 2015 Paris Climate Agreement, often called the Paris Accord, took a different approach. Instead of mandatory emissions reductions, each country is to voluntarily make emissions reductions. This shift led to the successful development of the treaty, which is the most ambitious climate agreement to date, and has been the cause for much hope and optimism. The goals of the Paris Accord are to keep global warming to below 2 degrees Celsius relative to pre-industrial levels. Recall that 2 degrees Celsius is the level at or beyond which we are likely to reach planetary threshold that will lead into a hothouse Earth scenario. However, warming of 2 degrees Celsius will still lead to major disruptions to many cities and countries around the world, and bring us into range of triggering many tipping points, any one of which could send us quickly over the threshold. Even at 2 degrees C, some small, low-lying nations and coastal cities will all but disappear beneath the rising seas. Thus, UN delegates agreed to an aspirational goal of limiting warming to 1.5 degrees Celsius, which would result in significantly less disruption. All this is good, very good, and it's a reason to be hopeful. There have, however, been some setbacks. To begin with, one of the first actions taken by Donald Trump as president was to declare that the United States would not sign the Paris Accord and would withdraw from the agreement. That puts us in a category with Syria and Nicaragua, the only other nations refusing to sign the accord. Nicaragua and Syria are minor players in terms of greenhouse gas emissions, but the United States is the second largest emitter of greenhouse gases, at 14% of all global emissions. China leads at 29%. The other issue with the Paris Accord is that despite significant promises from several countries, not enough nations have volunteered to cut back enough emissions to reach climate targets yet. This graphic from September 2019 illustrates where we are in the progress of signatory nations volunteering enough emissions reductions to keep warming below the 2 and 1.5 degrees Celsius thresholds. It's a busy, complicated graphic that you can study on your own if you want, but the bottom line is that right now in early 2020, we're not on track for meeting the goals of the Paris Accord. Instead, we're on track for substantial global warming this century, warming that will likely push Earth to the brink of entering a hothouse Earth climate scenario, and that would likely last for many centuries, possibly millennia. Given all this, you might wonder why people are not rioting in the streets demanding action. Well, actually, civil protests have become much more common in recent months. If people demand action, governments will provide the policies we need. Here in the US, not enough people believe climate change should be a top priority. However, it's worth noting that according to the Yale Program on Climate Change Communication, about 6 in 10 Americans believe that climate change is changing. The disconnect is that only about 4 in 10 Americans believe that climate change will affect them. And yet, the evidence is quite clear that climate change is already impacting us in dramatic ways. This is a list of the major ways that climate change is impacting and will impact the Southeast. I've posted on Moodle a video lecture about climate change's impacts on the Southeast. It's an optional video, but I recommend it for those of you who care about the region and or plan on living here after graduation. Finally, a lot of the science and the news on climate change is pretty gloomy, if not downright scary. It's essential to keep in mind that changes like those that we need begin slowly at first and then accelerate rapidly. In truth, there's far more reason to be hopeful now than there was just a few years ago. I've assembled a short list of hopeful topics for you to explore here on your own, if you would like. If you want to be in contact with others on campus who are concerned about climate change, join the BSc Climate Change Interest Group. It's a group of students, staff, and faculty who work to educate and empower each other on issues related to climate change. Just email me, Dr. Duncan, if you want to join or learn more about the group.